It just was such a huge dichotomy. Nobody was expecting that at all.
Ever wondered what's on the other side of the moon? Picture yourself as a scientist, seeing photos of the moon's far side for the first time. Prepare to be surprised. The hidden part looks completely different, covered in countless craters that no one expected. This discovery is not just changing what we know about the moon, but also raising new questions. Space used to be a big mystery, but now, thanks to technology like the James Webb Telescope, we're exploring it like never before. Come with us on a journey through space, where every new discovery opens up a world of possibilities. What is dark side of the moon? For centuries, humanity has gazed at the moon and marveled at its beauty. Yet, despite all our wonder and exploration, we have only truly explored one side of it. There's a whole other side we rarely see, often called the dark side of the moon. But why is it called that? And why has it stayed so mysterious? It all starts with something called tidal locking. The Earth's gravity has slowed the moon's rotation so much that the same side always faces us. This means the other side, which we can't see from Earth, is the far side of the moon. Sometimes we can catch glimpses of the far side's edges thanks to a slight wobble called libration. In total, about 59% of the moon's surface is visible from Earth at different times, but the far side remains mostly hidden. People often think the moon doesn't rotate, but that's not true. If it didn't rotate, we'd see all sides of it as it orbited Earth. In reality, the moon does rotate, but its rotation period matches its orbit around Earth. So, it takes about 29.5 Earth days for the moon to complete one rotation and one orbit, making its day and year the same length. The phrase dark side of the moon doesn't mean it's dark as in no light. It means dark as in the unknown. Before we sent spacecraft around the moon, we had never seen this side. Both sides of the moon get almost the same amount of sunlight on average. However, sunlight reflected from Earth, called Earthshine, makes the near side a bit brighter. During lunar eclipses, the far side gets slightly more sunlight because the near side is blocked by Earth's shadow. At night, when the Earth is full as seen from the moon, the near side gets about 10 lux of illumination. This is similar to a city sidewalk under streetlights and 34 times more light than a full moon provides on Earth. In contrast, the far side during lunar night gets only about 0.001 lux of starlight. Only when we see a full moon from Earth is the entire far side completely dark. The term dark also applies to communication difficulties. When spacecraft go behind the moon, they lose contact with Earth. This communication blackout happened during the Apollo missions and highlights another reason the far side is considered dark. So the far side of the moon remains a mysterious and intriguing place, not because it's dark and shadowy, but because it's largely unknown and challenging to explore. With advances in space technology, we're slowly uncovering its secrets, revealing a world that's been hidden from us for so long. Difference between the two sides. The moon's two hemispheres look completely different. The near side is dotted with large, dark plains called maria, which early astronomers mistakenly thought were seas. On the far side, however, the surface is densely cratered with very few maria. In fact, only 1% of the far side is covered by maria, compared to 31.2% on the near side. Scientists believe this difference is due to a higher concentration of heat-producing elements on the near side, as shown by data from the Lunar Prospector's gamma-ray spectrometer. Other factors like surface elevation and crust thickness also play a role, but don't fully explain why the far side's South Pole Aitken Basin, despite its low elevation and thin crust, wasn't as volcanically active as the near side's Oceanus Procellarum. One intriguing theory suggests that the differences between the two hemispheres might be the result of a collision with a smaller moon that formed from the same giant impact that created our moon. This collision could have added a thick layer of material to the far side. However, the far side's chemical composition doesn't fully support this idea. The far side of the moon has more visible craters, not because Earth shields it from impacts, but due to differences in lava flows. Lunar lava flows on the near side cover and obscure craters, making them less visible. National Aeronautics and Space Administration notes that Earth only blocks a tiny portion of the sky from the moon's perspective, so both sides receive similar numbers of impacts. The near side just has fewer visible craters, because lava flows have resurfaced it. Recent research suggests that when the moon was forming, heat from the nearby Earth kept the near side warmer for longer. This delayed the solidification of the crust, making it thinner. Meteoroid impacts on the near side could break through this thinner crust and release lava, forming the Maria. On the cooler far side, the crust thickened sooner, making it less likely for impacts to release lava. The far side also has more extreme variations in terrain elevation. The moon's highest and lowest points and its tallest mountains are all on the far side. Until the late 1950s, we knew very little about this hidden hemisphere. Librations, or small wobbles in the moon's orbit, gave us occasional glimpses of the far side, but only up to 59% of the total surface, and from such a low angle that it was hard to distinguish craters from mountains. One far side feature visible through libration is Mare Orientale, a huge impact basin almost 1,000 kilometers wide. It wasn't even named until 1906, and its true nature was only discovered in the 1960s when images were projected onto a globe. The Soviet probe Luna 3 took the first photographs of the far side on October 7, 1959, revealing a landscape with fewer Maria than expected. These images allowed the creation of the first atlas of the far side, published by the Union of Soviet Socialist Republics Academy of Sciences in 1960. In 1961, the Union of Soviet Socialist Republics released the first globe featuring far side lunar features, based on Luna's 3 images. Another Soviet probe, Zond 3, sent back higher quality images in 1965, showing chains of craters but still no extensive Maria. The second part of the Atlas of the Far Side of the Moon was published in 1967, based on Zond 3 data, and included 4,000 new features. That same year, the first comprehensive map and updated globe, featuring 95% of the lunar surface, were released in the Soviet Union. Most of the far side features were named by Soviet scientists, who chose many non-Soviet names, like Jules Verne and Marie Curie. The International Astronomical Union later accepted many of these names. National Aeronautics and Space Administration's Ranger 4 was the first spacecraft to impact the far side on April 26, 1962, but it failed to send back data. The most detailed early survey was by National Aeronautics and Space Administration's Lunar Orbiter program from 1966 to 1967, with Lunar Orbiter 5 providing most of the far side coverage. The far side was first seen directly by human eyes during the Apollo 8 mission in December 1968. Astronaut William Anders described it as looking like a heavily used sand pile, full of bumps and holes. All 24 astronauts from Apollo missions 8, 10 through 17 saw the far side, and multiple lunar probes have photographed it. Communicating with spacecraft on the far side is challenging because they are out of direct radio contact with Earth. During Apollo missions, this caused tense moments until the craft reappeared. Geologist astronaut Harrison Schmitt lobbied for Apollo 17 to land on the far side, but the National Aeronautics and Space Administration rejected the idea due to the risks and costs. In 2018, China launched the Keqiao Relay satellite to the Earth-Moon LTU point to facilitate communication with the Chang'e 4 lander and Yutu-2 rover on the far side. This point is also considered ideal for a proposed propellant depot for future space missions. China's Chang'e 4 spacecraft. In January 2019, history was made when China's Chang'e 4 spacecraft gently touched down on the enigmatic far side of the moon. This groundbreaking achievement marked humanity's first soft landing on this unexplored lunar territory. Equipped with advanced scientific instruments, including a low-frequency radio spectrograph and geological tools, the mission aimed to unravel mysteries hidden in the moon's secluded realm. Unlike the familiar near side, which constantly faces Earth, the far side offers a unique sanctuary from terrestrial radio interference, making it an ideal haven for radio astronomy. This advantage allows astronomers to peer deep into the cosmos without the disruptive hum of our planet's signals. In a remarkable development in February 2020, Chinese scientists unveiled high-resolution images captured by the lunar penetrating radar aboard the Yutu-2 rover. These images provided unprecedented insights into lunar ejecta formations, offering a glimpse into the moon's geological history and internal structure. Such revelations pave the way for a deeper understanding of lunar evolution and planetary dynamics. Building on these successes, the China National Space Administration launched Chang'e 6 in May 2024, marking another milestone with the first-ever lunar sample return mission from the far side's Apollo Basin. This ambitious endeavor involved a multifaceted approach, deploying a mini-rover for infrared spectroscopy and achieving robotic rendezvous and docking maneuvers in lunar orbit. The mission culminated in the safe return of lunar samples to Earth, heralding a new era of lunar exploration and scientific discovery. Looking ahead, the National Aeronautics and Space Administration and the United States Department of Energy are collaborating on the Lunar Surface Electromagnetics Experiment lander, scheduled for potential deployment by 2026. This robotic observatory aims to explore the moon's far side, measuring electromagnetic waves dating back to the universe's infancy. Such endeavors promise to uncover crucial insights into cosmic origins and the early universe's evolution. The far side of the moon also presents promising prospects for future astronomical installations, including radio telescopes nestled within its serene, crater-dotted landscape. These installations could harness the moon's natural shielding from Earth's radio transmissions, offering an unparalleled vantage point for observing celestial phenomena. However, before these visions can be realized, significant challenges must be addressed. The moon's fine dust poses a persistent threat to equipment and instruments, necessitating innovative solutions for contamination control. Furthermore, the materials used in constructing lunar observatories must withstand the harsh realities of space, including solar flares and cosmic radiation. Beyond scientific exploration, the moon's South Pole Aitken Basin stands as a tantalizing target for future sample return missions. This colossal impact crater, spanning nearly 2,400 kilometers, offers a unique window into the moon's geological past. Samples retrieved from this region could unlock invaluable insights into lunar composition and the cataclysmic events that shaped its surface. Moreover, the far side's Maria, shielded from the solar wind by Earth, harbors significant concentrations of helium-3, a rare isotope with potential applications in future fusion reactors. This valuable resource underscores the moon's potential role in advancing sustainable energy solutions and fostering human settlement beyond Earth. Mysteries of the dark side of the moon. In a groundbreaking new study, scientists from institutions spanning the globe have delved deep into the moon's mysterious geological past, unearthing compelling evidence to shed light on the long-standing enigma of its dark side. The research, spearheaded by experts from the Earth Life Science Institute at Tokyo Institute of Technology, the University of Florida, and other esteemed organizations, has revolutionized our understanding of lunar asymmetry. This asymmetry, characterized by stark differences between the moon's near and far sides, has baffled astronomers for decades. Through a meticulous blend of experiments, sophisticated computer modeling, and meticulous analysis of lunar surface data, the team uncovered a pivotal factor: radioactive elements. Elements like potassium, thorium, and uranium were found to play a crucial role, generating heat through their natural decay processes. This heat, in turn, melted the rocks where these elements were concentrated, leaving distinctive geological imprints across the moon's surface. Dr. Matthew Lanneville, a prominent planetary scientist and co-author of the study, highlighted the significance of these findings. The moon's near side exhibits unique concentrations of radioactive elements such as uranium and thorium, which are unmatched elsewhere on its surface. Understanding the origins of these local enrichments is key to unraveling the moon's early history and, by extension, providing insights into the conditions prevailing in the nascent solar system and early Earth. Furthermore, the researchers identified another crucial player in this lunar mystery: creep. Short for potassium, rare earth elements, and phosphorus, creep-enriched materials have been linked to lunar Maria, vast plains formed by ancient volcanic activity. These materials possess lower melting points, contributing significantly to the moon's evolving geological landscape over billions of years. The implications of this study are profound. It suggests that creep-enriched Maria have been dynamic agents of change since the moon's tumultuous infancy. Their volcanic origins and unique chemical composition have shaped the lunar terrain, leaving lasting marks that preserve crucial clues about our solar system's early evolution. Moreover, the research underscores the moon's role as a cosmic time capsule. Unlike Earth, which has undergone extensive geological transformations due to erosion and plate tectonics, the moon's surface remains remarkably pristine. Its geological record, etched with the remnants of ancient impacts and volcanic activity, offers a rare glimpse into the early epochs of our celestial neighborhood. As our understanding of the moon's geological history continues to deepen, so too does our comprehension of Earth's origins. The moon, with its unaltered surface and geological archives, stands as a sentinel from the past, holding secrets that could unlock pivotal insights into the formation and development of our own planet. Discoveries made on the far side of the moon. Since the historic landing of China's Chang'e 4 lander on the far side of the moon, humanity's view of our celestial neighbor has been forever changed. The mission, conducted by the Chinese National Space Administration, marked a monumental leap in lunar exploration. It offered a unique glimpse into the mysterious dark side of the moon, a term often used to describe its hidden hemisphere. Capturing mesmerizing images and extracting crucial mineral samples, Chang'e 4 provided unprecedented insights into the lunar surface. The findings eagerly awaited and recently published in the Journal of Geophysical Research. Planets unveiled a complex lunar landscape. Layers of dust, soil, and fragmented rocks comprise the top 130 feet, shedding light on the moon's geological history. Among the remarkable discoveries was a crater, evidence of a colossal impact that shaped the moon's surface eons ago. Jiangqing Feng, an astrogeological researcher, highlighted the significance of this finding. Collaborating with experts, Feng identified 5 distinct layers of ancient lunar lava, remnants of volcanic activity that once reshaped the moon's terrain billions of years past. The moon itself, formed approximately 4.51 billion years ago from a cataclysmic collision between Earth and a Mars-sized celestial body, has endured millennia of cosmic bombardment. These impacts scarred its surface, creating the familiar features we see today, such as craters and ridges. Similar to Earth, the moon harbored molten magma beneath its surface, erupting through fractures caused by impacts. This volcanic activity, crucial in shaping the moon's early landscape, gradually diminished over time. Feng's analysis suggests that the moon's volcanic activity ceased between 1 billion to 100 million years ago, rendering it geologically dead by current standards. However, intriguingly, the data from Chang'e 4 hinted at the possibility of subsurface magma reservoirs, challenging previous assumptions about the moon's dormant state. This revelation opens new avenues for exploration and understanding of lunar geology. Looking forward, Chang'e 4 continues its mission, promising further groundbreaking discoveries. Feng and his team envision an expansive mapping endeavor, unraveling more mysteries hidden beneath the moon's ancient surface. As humanity's exploration of the moon progresses, each discovery brings us closer to comprehending our lunar neighbor and its pivotal role in our cosmic history. How the James Webb Space Telescope has influenced astronomy. To explore more about the dark side of the moon, a special telescope was designed, one of which was the James Webb Space Telescope. This space observatory isn't just any telescope. It's a revolutionary leap in our ability to explore the cosmos, particularly in the realm of infrared astronomy. Launched on Christmas Day in 2021 atop an Ariane 5 rocket from French Guiana, James Webb Space Telescope made its way to a unique orbit near the Sun-Earth L2 Lagrange point, about 1.5 million kilometers away from Earth, arriving in January 2022. Its mission is to delve into the universe's deepest secrets with unparalleled clarity and precision. Developed under the leadership of the National Aeronautics and Space Administration, alongside the European Space Agency and the Canadian Space Agency, the James Webb Space Telescope boasts an impressive array of capabilities. Unlike its predecessor, the Hubble Space Telescope, James Webb Space Telescope specializes in capturing infrared light, ranging from long-wavelength visible light to mid-infrared, spanning from 0.6 to 28.3 micrometers. This allows the James Webb Space Telescope to peer through cosmic dust clouds, unveil the formation of the first galaxies, and analyze the atmospheres of distant exoplanets, tasks previously impossible due to limitations in detecting infrared emissions. Central to James Webb Space Telescope's design is its massive 6.5-meter diameter primary mirror, composed of 18 hexagonal segments coated with gold-plated beryllium. This mirror's significant size provides a light-gathering area approximately 6 times larger than Hubble's, enabling unprecedented observational power. However, to function optimally, it must maintain an extremely cold temperature below 50 Kelvin, achieved through a sophisticated 5-layer sun shield that shields it from the sun's heat and other celestial sources. The journey to its completion was arduous and costly, beginning with initial designs in 1996 under the name Next Generation Space Telescope. Despite setbacks, including budget overruns and technical challenges, the telescope finally emerged as a testament to human ingenuity and determination, culminating in its triumphant launch. Since its eagerly awaited first images were unveiled to the world on July 11, 2022, this telescope has rapidly transformed our understanding of the universe. "It's changed so much," remarked one astrophysicist, emphasizing how the James Webb Space Telescope has ushered in a new era of discovery by pushing the boundaries of observational astronomy. The telescope's ability to peer back over 13.4 billion light-years allows scientists to glimpse the earliest galaxies ever observed, some forming mere hundreds of thousands of years after the Big Bang. One of this telescope's standout achievements is its capability to observe in infrared, which reveals celestial objects' thermal emissions. This unique perspective not only enhances our understanding of distant galaxies, but also offers insights into the composition and evolution of planetary atmospheres, such as the recently analyzed exoplanet WASP-96b. The telescope's spectroscopic analysis of this distant world's atmosphere provided astronomers with unprecedented detail, underscoring JWST's pivotal role in advancing exoplanetary science. Looking ahead, the James Telescope promises even more groundbreaking discoveries as it continues to explore the depths of space. Scientists eagerly anticipate unexpected findings that could reshape current theories about the universe's origins and evolution. As this telescope enters its second year of operation, the excitement among researchers is palpable, driven by the prospect of uncovering new cosmic mysteries that defy conventional understanding. For the National Aeronautics and Space Administration, this telescope represents a cornerstone in its quest to uncover the secrets of the universe's dark side, literally. By focusing its powerful instruments on the elusive dark side of the moon, the National Aeronautics and Space Administration aims to unravel long-held mysteries about lunar geology, potential resource deposits, and the moon's ancient history. Future exploration of the moon's dark side. The future of lunar exploration holds promise far beyond our celestial neighbor. Imagine a radio telescope nestled on the hidden far side of the moon, a beacon of scientific potentiality. This ambitious concept, spearheaded by the National Aeronautics and Space Administration's Artemis program, aims to transcend the limits of current astronomical instruments. Why the moon's far side? It's a sanctuary from the Earth's radio chatter, a pristine locale shielded from human interference, as physicist Stephen Kahn explains. Existing telescopes like the James Webb Space Telescope struggle amidst terrestrial noise, but a lunar counterpart could unlock unexplored cosmic frequencies, delving into epochs obscured by the noise of history. Enter the Lunar Crater Radio Telescope, a visionary project led by Saptarshi Bandyopadhyay. Picture a colossal 350-meter dish nestled within a lunar crater, primed to capture ancient radio waves from the universe's dawn. This isn't just stargazing, it's peering back to the cosmic dark ages, an era before stars ignited when hydrogen clouds dominated the cosmos. Here, the moon's quiet expanse shields against Earth's atmospheric interference, offering a pristine canvas for scientific inquiry. The telescope's deployment reads like lunar origami. Cables anchored in the regolith unfurl a mesh dish, while a spacecraft overhead acts as a relay, facilitating data transmission. It's an intricate ballet of technology, poised to redefine our understanding of cosmic origins. Yet this lunar venture faces hurdles familiar to ambitious science missions. Funding remains a critical juncture, with the telescope in National Aeronautics and Space Administration's innovative advanced concepts phase, bolstered by $500,000 in developmental support. However, the path to billion-dollar budgets hinges on a resounding scientific consensus, a testament to its potential impact. Why now, and why the moon? Deeper dives into lunar exploration underpin the National Aeronautics and Space Administration's strategic vision, mirrored in initiatives like the Commercial Lunar Payload Services. These endeavors promise over 50 payloads to our celestial companion, including seismic suites and heat probes probing lunar mysteries. At Schrödinger Crater, a cosmic laboratory awaits, its geological record holding clues to lunar evolution and planetary formation. For planetary scientist Deborah Needham, Schrödinger is a prime target, its colossal impact crater an open book on lunar history. The Farside Seismic Suite listens to moonquakes, unraveling lunar interior secrets, while the Lunar Interior Temperature and Materials Suite probes its core temperature. Meanwhile, Lucy ventures into the moon's exosphere, studying cosmic dust and ionized particles, shedding light on lunar weathering processes. This scientific ensemble mirrors China's Yutu-2 rover, a trailblazer on the moon's far side since 2019, traversing von Karman crater's uncharted terrain. It's a testament to international collaboration and lunar exploration's global frontier. Looking ahead, the Lunar Radio Telescope symbolizes more than technological prowess. It's a quest to understand our cosmic roots. As Kahn notes, its niche focus must align with broader scientific priorities, advocating for its pivotal role in forthcoming astronomical surveys. This mission isn't just about seeing farther. It's about peering deeper into the universe's infancy, decoding its elemental origins. We hope you enjoyed this video. Stay tuned for more.